Okay, so welcome to this next video in the playlist on probability. In this video what we're going to discuss is the beta distributions, which is a whole family of distributions which are often used as priors in Bayesian statistics. Okay, so the beta distributions is the topic for this video. So let me just remind you of what a prior is in Bayesian statistics from the previous videos. So in Bayesian statistics what we start off with is we do not know a probability parameter. So there is some unknown probability parameter. In the Laplace's rule of succession, what we had was we did not know that the probability parameter that the sun would rise on a given day. Okay, however, we have some probability distribution for how it occurs. Laplace chose to begin with the uniform distribution, i.e. he chose to believe that any probability between 0 and 1 was equally likely as the probability parameter for the sun rising on a particular day. However, you could choose a different distribution, and more generally this is called the prior distribution. So what you know at the start of your experiment about how the parameter p is distributed, basically. Okay, then what you do is you say, we've done some experiment, and for every single value, what we do is we construct a probability space, and for every single value of p between 0 and 1, so here is the interval 0 to 1, for every single value there, you can then put in a bunch of outcomes. So, for instance, in the Laplace's rule of succession, the outcomes of the experiment were if we watch the sun, if we observe the sun rising on little n days, then there's every single possibility of how the sun can rise and not rise on any day. So firstly, there are basically two dimensions to this problem. Firstly, we don't know the probability parameter, and if you do select a probability parameter, for each probability parameter, each possible value the probability parameter could take on, there's absolutely loads of outcomes. Well, there's not loads of them, but there's 2 to the n of them, 2 to the n possible outcomes with that probability parameter, and for every single possible probability parameter these outcomes are all repeated, and of course each of the outcomes in that for each of these ones. So let's say we have 2 possible values of the parameter here, so let's say this is 0.2 to make it concrete, and this one's 0.5. Then within each one of these, so this is the event that the probability parameter is 0.2. Within that event, so if I zoom it up over here, there will be every possible outcome of whether the sun rises on each of the possible little n days. So for instance, an outcome in here will be that it doesn't rise for all little n days. So it doesn't rise, etc. for all little n days. Another possible outcome will be that it rises on the first day and then doesn't rise for all the rest of the days, etc. And there's going to be every possible outcome, every single possible possibility of how the sun can rise or not rise on each of these days. So in each position for each day, the sun can either rise or it can't rise. For the second day, it will be rise or not rise. So the total number of possible outcomes here is two possibilities for the first thing. For each of those possibilities, there are then 2 possibilities for the second one. For each of all of those 4 possibilities, there's then 2 possibilities for the third one, etc. So you keep going on to the nth 2. So you find, okay, that overall in each one of these events, so fix a probability parameter. So in this case 0.2. For that probability parameter, there are 2 to the n little events. Okay, 2 to the n little outcomes within that event. Similarly, in 0.5, all of these outcomes are again within this event that the probability parameter is equal to 0.5. But of course, in this one, the probability of a certain outcome is going to be different in here. The probability, for instance, of the sun rising all little n days is going to be higher if the probability parameter of it rising a certain day is 0.5 as opposed to if it's 0.2. So basically what we know is that if you are given a certain probability parameter, so if you set up a random variable x which ascribes to each outcome in this entire probability space the number of days on which the sun rises, so it ascribes some real number, in fact ascribes an integer ranging from 0, 1, 2 all the way up to little n, because the those are all the possibilities of how many times the sun can rise on each outcome. Then basically if you condition on knowing the value of p, so basically what you do is you say, okay, I'm not interested in the rest of the probability space now, I'm just interested in this strip. I'm saying we now know the probability parameter, I'm saying it's 0.5, we're conditioning on that, so we say what is x conditional on p equaling 0.5 basically, and of course we know that that's going to be binomially distributed now, and that with number of trials little n, and probability parameter is now equal to 0.5. So conditionally it's very, very simple, but obviously the larger probability space is more complicated because we don't know p. And basically what we then want to do in Bayesian statistics is say, okay, we then we now observe the sun rising on these little n days. So we know that the sun has risen for the past little n days. So we now limit our attention only to those outcomes in which the sun rises for n days. So rise, 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 little n times. Okay? So for each one of these probability parameters ranging from 0 to 1, each one of them as an event contains somewhere in this set, it contains the outcome that it rises on all little n days. Basically I'm saying go through every probability parameter, pick out those outcomes and put them all into a set together, and we are saying that that event happened basically. And then what you do is you say, okay, now let's condition on that event having happened, which is the event that x was actually equal to little n. We're saying we're going to condition on that, and now what we want to find is what is the probability density function of p given that this event has happened. So basically get rid of the rest of this probability space. So I'm not interested in all of this now, I'm just saying this has happened. Okay, we still have this random variable ascribing probability parameters to each of these outcomes in here. What now is the probability density function of that random variable, which is ascribing to each outcome the probability parameter that was used, given that this event has happened. And basically that new distribution is called the posterior distribution in Bayesian statistics. And obviously we know that in the case of Laplace's rule of succession, what will happen is that it will typically, if we're given that the sun has risen for the past 10 days, the probability distribution starts to look more like that, i.e. it tilts towards the higher values over the lower values. Okay, so basically the importance of the beta distributions is that why should we start off thinking that that the probability parameter of the sun rising on a certain day is uniformly distributed? Obviously Bayesian statistics goes beyond just this example of the sun rising. It's basically whenever you've got some unknown probability parameter, you start off with an initial probability distribution for that probability parameter, you get some experimental evidence, and now based on that experimental evidence you want to update it to a new probability distribution for that probability parameter called the posterior distribution. But we might not want to start off with a uniform distribution. We might want to start off with a different distribution. And of course you could start off with any distribution on 0 and 1. The beta distribution are very nicely behaved, and they're often quite easy to use in Bayesian statistics, and they are defined on 0 to 1 basically. So and we're going to see how effectively they are a generalization of the uniform distribution on 0 and 1. Okay, so with that, let's define what the beta distributions are. So if you have some random variable, okay, so we'll say that this p is a random variable, so just think of it like this example here, where we're ascribing each outcome in this abstract probability space here, we're ascribing it the probability parameter it was associated with. So all of these events, all of these outcomes, in this event that the probability parameter was 0.2 will obviously be ascribed the number 0.2 by the random variable p basically. So I could draw in a p here ascribing to each outcome a number between 0 and 1. Okay, so let's say p, which is a random variable like this, is beta distributed with parameters a and b. Okay. So there are two parameters, which is why it forms a whole family of distributions, because you can vary a and b. What that means is that the probability density function for this beta distribution as a function of x is going to be equal to 0 if x is not an element of 0, 1, okay? and in fact, actually, we'll leave it at that for now, but often it's going to be easier to just define it on the open interval 0 to 1. Obviously, that doesn't really change much, but it will, on some of the functions we're going to have, will not be defined at the points 0 and 1. So it's easier just to omit them, basically. So we'll define it instead on the open interval 0 to 1, and that means basically that we're saying the probability can never equal 1 and the probability can never equal 0. And intuitively that should be pretty obvious, because, well, maybe not, but can probabilities ever equal 0? Is there really probability nothing that an event will ever happen? Can we ever say that, really? And similarly, can we ever say that the probability is absolutely certain? No. So omitting 0 and 1 is actually done because to make it mathematically simpler, but you can sort of try and justify that from an intuitive point of view if you like. Okay, and then as far as integrating the probability distribution is concerned, it's not going to make any difference because the points 0 and 1 have length 0, or if you know measure theory, they have the Bayesian measure 0. Okay, so on the interval 0 to 1, what are we going to define it? That's what it is not on the interval 0 to 1. On the interval 0 to 1, it's going to be defined to be x to the power, missed off a bit, the normalizing constant, which I'm going to tell you how to work that out in a moment, x to the power of a minus 1 times 1 minus x to the power of b minus 1 if x is an element of this interval 0, 1. Okay, so the best way to get a feel for this is to do some examples, basically. So that's what we're going to do. We're going to start off with, and I should tell you, these values a and b, what values can they take on, basically? There are some restrictions. A needs to be greater than 0 and b also needs to be greater than 0, and they both need to be real numbers. Okay? Right, and when I first saw that, I was a bit surprised. A greater than 0, b greater than 0. You see, what I would have expected is that you'd have wanted a to be greater than 1 and b to be greater than 1, because you want there to exist some normalizing constant here. This normalizing constant, by the way, is whatever you need to make it in order to make sure that this integrates to give you 1, basically. So let's just briefly discuss this normalizing constant. So, if this is going to be a probability distribution, we want the integral from negative infinity to infinity of this probability density function, dx, to equal 1. Now, except on the interval 0 to 1, it is equal to 0 everywhere. If I integrate 0, I get 0. So in fact, this integral, I want this to be equal to 1. This integral becomes the integral from 0 to 1 of this bit, because on the interval 0 to 1, it is equal to this. So we'll put in that. C times x to the power of a minus 1, 1 minus x to the power of b minus 1 dx. Okay? Right, so pull out the normalizing constant. This becomes c times the integral 0 to 1 of x to the power of a minus 1, 1 minus x, let me just pull this up over here, 1 minus x to the power of b minus 1 dx. Oh dear, that's a bit messy. Right, so I don't yet know, if you give me an a and a b, I, in principle, can work out this integral if it exists, and we'll discuss that in a moment. Therefore, this normalizing constant is just going to be 1 divided by that integral. If I bring this over to the other side and divide through by it, so I get that the normalizing constant is the 1 over the integral from 0 to 1 of x to the power of a minus 1, 1 minus x to the power of b minus 1. So basically, if you choose an a and a b, so you give me a specific a and a specific b, the normalizing constant is set. It cannot take any old values. Once you've set a and b, it takes on this value here, and you can compute it. It's whatever you need to put there in order to make sure that this integrates, this PDF integrates to 1, basically. Okay, so now let's have a bit of discussion about why it is that a and b can take on values greater than 0. So a and b are greater than 0, and I will drop writing the PDF basically now. I'll just write it as cx to the a minus 1, 1 minus x to the b minus 1. So that's on the understanding that I mean specifically on the interval 0 to 1. Everywhere else it's 0, but it gets a bit of a faff to write out 0 if x is not an element of 0, 1. So I'm writing this out on the understanding that that's on the interval 0, 1. Okay, right. So a and b are greater than 0. You see, that surprises me, because if I make a value like a is equal to a half, and let's for simplicity say that b is equal to 1, then my function becomes c to the times x, and then I stick in a half here, and I get half minus 1, and then I stick in 1 over here, and luckily that gives me 1 minus 1, and that just gives me something to the power of 0. And this is why I was picking about whether we wanted the open or closed interval. You see, if I have, this basically becomes to the power of 0. Now, any number to the power of 0 is 1, with one exception, the value 0. If I plug in x is equal to a 1 there, I would get 0 to the power of 0. Now, that's not defined. You can't even define it using analysis. It approaches different things. The limit approaches different things. If it doesn't approach anything, basically. The limit doesn't exist of the function x to the power of x as x approaches 0. In the complex plane, anyway. It does exist in the real line, but in the complex plane it doesn't exist. Basically, you run into problems very quickly if you try and define 0 to the power of 0. So we've inverted that, we've circumvented that by just saying we won't use the points 0 or 1. And similarly, if we have this one, if you let a equal 1, then you'll get to the power of 0 here. And again, if x is equal to 0 there, you'll have the same problem, 0 to the power of 0. So basically, we've omitted that problem by just defining it on the open interval 0 to 1, and that's why we did that. Okay, so since we're not using the point 1, we can just replace that with 1. Then we've got is equal to c x, a half minus a half is to the power of negative a half. So overall, we get c over the square root of x, basically. And that function is going to blow up as x approaches 0. So it is true that it's going to have an asymptote as x approaches 0, which doesn't look very hopeful. I mean, how on earth are we going to standardise that? But it turns out that you can standardise that, because if we integrate between 0 and 1, c x to the negative a half dx, then just using basic calculus, the way that we would integrate this is finding the antiderivative. So it becomes c times the antiderivative of x to the negative a half. All you do is raise the power by 1 to get x to the half, and then divide through by the new power, which is a half. And then we're evaluating that between 0 and 1. Now, if we evaluate this at 1, we get c 2 times c, because dividing by a half is the same as multiplying by 2. And then sticking 1 there, you'll get 1. Then subtracting off the 0 bit, so I'll put in the 1 to the power of a half there, minus 2c times 0 to the power of a half. 0 to the power of a half is just 0, so that goes, and 1 to the power of a half is just 1. Of course, we're defining the square root function here, not to be this function here, i.e. it ascribes to 1. The square root of 1 is 1, not 1 or negative 1. Basically, if you define the square root function to be like that, that's not a function, because it ascribes to 1 point multiple points. That's not a function. So we take that bit off. So the problem of the square root of a number is not the same as finding the solutions to x squared is equal to 1. That's an important distinction to note, that the square root of 1 is not the same problem as x squared is equal to 1. Obviously, this equation has two solutions, x is equal to plus 1, x is equal to minus 1, but the square root of 1 is equal to 1. So don't let that confuse you. Don't think this is plus or minus 1. It is plus 1. Okay, so this gives us 2c. And obviously we want that integral to equal 1, so there is a normalizing constant. C will equal half. If you set c equal to a half, this integral will be equal to 0. And that, intuitively, is why we allow values of a and b that are greater than 0, basically. And they don't have to be greater than 1, because if they are greater than 0, then that implies that a minus 1 and b minus 1 are both greater than minus 1. And if the powers here are greater than minus minus 1, basically, even though you have you're potentially going to have asymptotes at 0, and in this case you'll have an asymptote at 1 if you've got a negative power there, because as you get closer and closer to 1, you'll get closer and closer to dividing through by 0 when 1 minus 1 is equal to 0. So you'll have an asymptote at both 0 and 1 potentially if these are both negative numbers. But as long as they are greater than minus 1, strictly greater than minus 1, when we integrate them, they still are normalizable. Their integrals still come out to be some finite value, and I, for one at least, find that quite extraordinary about those reciprocal functions where the power of the reciprocal is less than 1, that when you integrate them, they're still going to go back to, they're going to basically go back to being positive numbers, and when you evaluate those at 0 and 1, well, at 0, it's fine, basically. Okay, so that intuitively is why we allow values between a and b to be greater than 0 and don't insist that they have to be greater than 1 to make these powers positive. So we can basically have functions which blow up at 0 and 1 as long as when you integrate them they are still normalizable, and that's why we can't let the powers we can't let a and b be less than 0, because if they or equal to 0 in fact, because if they were equal to 0 or less than 0, when you integrate them you'll still end up with so for instance, when you integrate x to the negative 2, you'll still end up with x to the negative 1 basically. So when you evaluate that at 0, it's still going to blow up, so there the area isn't normalizable. Okay, right, so I think we will cut the video there, and in the next video what we'll do is some specific examples of the beta distribution. So we'll pick out some specific values for a and b and see some specific examples. I mean, we've already done one, we've seen this one here, which was the one corresponding to a is equal to a half and b is equal to 1, but we'll see some more examples in the next video.